test for the mean for large samples, greater than, equal to 30. Remember, that's our same criteria that we used for confidence intervals. We're going to use the exact same thing here. So in other words, if more than 30, I'll never use 30 exactly, but more than 30 we'll treat as a z distribution based on the central limit theorem. Now, we looked at p-value briefly in the last section, and we'll see a lot more in this section. But suppose you had calculated a p-value, and we're going to compare it with whatever the level of significance alpha is, which that is a number that's given to you in the problem. And it's real straightforward and pretty easy. If the p-value is less than or equal to alpha, you will reject your null hypothesis. Then if your p-value is greater than alpha, you'll fail to reject the null. I think it's very unlikely that your p-value would ever actually equal your null hypothesis, so most of the time I'll just say less than or greater than, because I don't think we'll ever have one that's exactly equal. Not impossible, but unlikely. Now here's a p-value, another two-tailed one like we did from last section. Like I said, we will certainly see other ones that are they won't all be two-tailed. So this says find the p-value for a two-tailed test with z equals 1.72. And as I mentioned in the last section, the easiest way to do this, I just drew a little picture to show you the p-value will be the combined areas in both those regions. But as far as making the calculation is just look up the negative 1.72. Because that's exactly, remember, the area in the normal curves to the left. And if you look up negative 1.72 in the z chart, you should get 0.427. Multiply that by 2, you get 0.854. And there's another way, like I showed, do it in the calculator using the normal CDF if you want to. Whatever you prefer. Now, let's throw in there, so there's the p-value. Now, let's say we did have an alpha in the problem. Decide whether or not to reject the null if given a level of significance of 0.05. So what we do is compare our p-value to our null hypothesis test and put the p-value first. P-value 0.0854 is greater than 0.05. So if p-value is greater than alpha, we fail to reject the null. Now suppose we change the level of significance to 0.10. Decide whether or not to reject given alpha 0.10. Well, since 0.0854 is less than 0.10, we reject the null hypothesis. So there's an example where it was kind of critical what the level of significance was. And I just kind of mentioned this paragraph that statisticians would certainly prefer it to be a lot smaller p-value where you clearly reject, or a little bit larger to where you clearly not reject. It kind of gets a little, your conclusions can get a little tricky whenever you're kind of between numbers like this, but that's not really our concern right now. But now when I say large p-values are between 0 and 1, as I mentioned here, so like, 0.3, 0.4, that would be considered a pretty large p-value. There are probabilities. But not your concern worrying about whether it's a small or large p-value. Now we have how to perform a z-test for the mean, a hypothesis test for z's. Z distribution, n greater than 30, automatically a z regardless of whether or not we have the population standard deviation. And also remember, it doesn't really matter if the population is normally distributed, which we'll see in the next section that it'll have to be normally distributed for small samples, just like it did for confidence intervals. So everything's the same as far as our z and t criteria. Well, let's look at this test statistic here. X bar minus mu naught. X bar is our sample mean, mu naught's our hypothesized mean, as I mentioned in the beginning of last section, whatever we're testing against, divided by sigma, divided by square root of n. Now that formula looks pretty familiar. It looks just kind of like the way you calculate the z-score for random variable x bar, and it's pretty much what it is. Now there are two ways to perform a z-test. And we'll look at them in this order, using p-values, and then another method using rejection regions and critical values. So the first one we'll focus on is strictly p-values. So we're going to take our sample data. Of course, we'll determine whether it's left-tailed, right-tailed, or two-tailed from the wording of the problem. And then we'll use that test statistic. We'll come up with our p-value, and then we'll compare it to our alpha, and that's how we'll reach our conclusion. That's basically the process here. So look at this example. You have one of your sales distributors reports an average 150 sales per day for the distributorship. Now, before I go any further, I'm going to go and identify what the hypothesis statements are. Average of, and you go back and look at those translations from the last section. Of and is are both an equivalent way to say equal. So this is clearly an equal. That's what they're claiming. Equal pairs that were not equal. And remember, that was named a two-tailed test that we learned before. All right. Okay, definitely two-tailed. So now we've got that set up. We can read the rest of the problem and then proceed from there. So we randomly select 35 days. So that's our N, sample size. The sample mean for those 35 days is 143 with a standard deviation of 15. It doesn't matter whether we have population or sample here. It's still going to be a Z because we're more than 30. Given a level of significance of 0.01, is there enough evidence to doubt the distributor's reported average? In other words, are we going to reject that claim that it's 150 based on that data? So in other words, we're not if we reject, we're not proving that it's wrong, but in our best estimate based on that data, we strongly would feel that it was wrong if we reject. Of course, like I was saying earlier, if we don't reject, that doesn't mean we totally agree with it, but we certainly don't have enough evidence to say it's wrong. So I kind of wrote all the sample data right here. There's your N, 35. X bar is 143, S is 15, alpha is 0.01, two-tailed test. So here's the test statistic. X bar goes first, 143, sample mean. Be careful that you always put X bar first because you have two different means up there in the numerator, and I have seen people, get these reversed. The second number will always be your hypothesized mean, your mu naught, what you're testing against. So sample mean first, hypothesized mean second. Then divided by 15 over the square root of 35, and you get a test statistic of negative 2.76. Two-tailed test, equal, not equal. So this is already negative 2.76. I drew a picture representing both ends. So we can look up the negative 2.76 on the chart, and we have to double it because that's half the p-value in each end. So it's 2 times area left of negative 2.76. Look up that on the chart. It's 0.0029. Multiply that by 2. It's 0.0058. 0.0058 is less than 0.01 because of that one extra zero in front. Therefore, we reject. So kind of putting this in more in a formal statement, we reject the claim that the mean sales per day is 150. Now, these numbers aren't too bad. Sometimes when you're going to get negative numbers, you'll see a little bit later, and these kind of weird decimal numbers, a little trick I like to use for comparing numbers, and if you're not always sure which one's the larger and which one's the smaller, like I said, more likely that'll be true with negatives, is what I like to do is take the number that you think is the larger number, subtract the other number. If you get a positive result, that means you were correct. That was the largest number. If you got negative, that would mean the other number was the larger number. Now, we have a calculator function that does this, just like we had for the sample mean, the confidence intervals. Now, this time we use what's called test, z-test. Okay, let's see. So we go stat, test, z-test. Now down there we have Z interval and T interval. So keep in mind that those are for confidence intervals. Now test will be for hypothesis test, so it's not too difficult to make the distinction. So you hit test, enter. Now you choose stats. Data would be only if you had data values in there. The hypothesized mean that we were testing against was 150. Standard deviation, I'm going to have to go back and look at these numbers. 143 is the mean, but that's not what they want first. They want the standard deviation, which was 15. $143. The N was 35. And what you choose here, it's always the alternative hypothesis. Be very, very careful. Those three choices are always whichever HA you have. So this case we have not equal. We hit calculate. And that should match what we have over here. And see our negative 2.76. And look at our p-value, 0.0058. And let's look and see. Yep, so there it is. There's the box on the right, and you see how I selected the not equal right here, and there's everything we need. All right, let's look down here at this next one. A manufacturer of sprinkler systems designed for fire protection claims that the average activating temperature is at least 135 degrees Fahrenheit. To test this claim, you randomly select a sample of 32 systems and find the mean activation temperature to be 133 degrees Fahrenheit with a standard deviation of 3.3 degrees Fahrenheit. Given a level of significance of 0.10, do you have enough evidence to support the manufacturer's claim? So let's see what they're saying. At least 135. So at least is always a null, and see I labeled that as my claim. That greater than or equal to always pairs up with less than. So this for sure is a left tail test. Right there. There we go. Now my sample data is all over here to the right. N is 32. 133 X bar, 3.3 is S, standard deviation 0.10. So calculating the test statistic using the formula. X bar 133 minus 135 for this hypothesized mean, divided by 3.3 over the square root of 32, which gives me negative 3.43. Okay, so finally we're doing one that's not a two-tailed test. So we did so many of those, we got used to multiplying by 2. We will not multiply this by 2 on a left tail or a right tail. So all we do is just look up negative 3.43 on the chart, or you can use normal CDF like I've done over here. It's fine. You look it up, it's 0.0003. Cut that off. There we go. That's your p-value. So you do not multiply this by 2 because it's not two tails, it's just left tailed. And there shows the calculator box. You notice that the main thing here is that this is, I picked my alternative was less than right here. And that's just scientific notation. Times 10 to the negative 4 means 3 zeros in front of it. So 0.0003. So now we compare that to alpha to make our decision. So 0.0003 is less than 0.10. We reject the claim that the activating temperature is at least 135 degrees Fahrenheit. So p-value less than alpha, we reject. So that doesn't prove they're wrong, but in our best statistical guess that claim is wrong. So let's look at the next one. Random sample of 85 8th grade students has a mean score of 282 and a standard deviation of 35 on a National Mathematics Assessment Test. This test prompts the state school administrator to claim that the mean score for the state's 8th graders in the exam, the average mean score is more than 275. If alpha equals 0.04, is there enough evidence to support the administrator's claim? So here we go, mean score, let's see, more than 275. So more than is greater than. Its alternative is less than or equal to. Claim is the alternative. So if we support that claim, that means we are rejecting the null to get to that claim. So I have the sample data written there. So let's look at our test statistic. We have 282 is x bar minus 275 divided by 35 over square root of 85, which is 1.84. This is a right-tailed test by definition of the 3 tests. So for a right-tailed test, also we don't double the value here. It will be the area to the right of 1.84, which I found the easiest way is to use symmetry in the normal curve. In other words, you can still look up negative 1.84 because it folds right over to the other side. If you look up negative 1.84 on the chart, you should get 0.0329. That is less than 0.04, so we will reject. So we actually reject the null hypothesis, and we do support the administrator's claim that the mean test score is greater than 275. And here are the outputs from the calculator. Okay, I'm going to skip over this problem. The answer is there. Come down here to the other method for testing is using what's called rejection regions and critical values. So now we're still going to use our test statistic, but you have to kind of completely ignore p-values for now to do this. So this time what our shaded area is going to represent is our shaded area actually represents the level of significance. So this being a left-tailed test, there's your alphas. In other words, if alpha was 0.05, for example, in a problem, the shaded area would represent 0.05. And the negative z alpha will be the value on the normal curve that translates to that area of 0.05, kind of like a reverse table lookup process. So what we're going to say for a left-tailed test is these are the shaded areas are called the rejection regions. So if your test statistic is a number that's smaller than this for a left-tailed test out here in the shaded area, you'll reject. The big open area, unshaded area, is fail to reject. So I labeled that fail to reject, but the shaded is called your rejection region. So let's just say if your critical value here was negative 1.96 and your test statistic was negative 2.5. Well, negative 2.5 would be less than negative 1.96, so we would reject. Well, let's say, for example, if it was negative 1.5, that would be on the other side of negative 1.96, and we would fail to reject. So right-tailed, same kind of idea, symmetric to the left-tailed. And we will reject if our test statistic is greater than our critical value, because it'll be to the right of it. And then once again with two-tailed, it's kind of a half and half thing. So like if your alpha was 0.05, your two-tailed, your values here, plus and minus, half of the alpha. So if it's 0.05, you get a 0.025 at one end and 0.025 at the other end. So these values that are from the normal curve are called critical values. I think I'll highlight that. Let's see. So that's what we call critical values. Now, for left-tailed test, critical value will always be negative. For a right-tailed test, the critical value will be positive. And then two-tailed test, you will always have a plus and minus pair. All right, so now let's come down here. What we'll formally define now as a decision rule. It's actually a statement sort of verbalizing what I was saying a minute ago. Like, for example, if a left-tailed test, if your test statistics to the less than your critical value, you reject. So now we're going to kind of formalize that in a statement. So in fact, any decision rule for a left-tailed test is going to start out, and we'll look at this example here in a second, but it's going to start out reject the null hypothesis H0 if Z is less than some number. Right-tailed test will be reject if Z is greater than some number. And then a two-tailed test will always be phrased with two numbers. You reject the null if your test statistic is less than the negative number or greater than the positive. Now this chart will be provided for you in the test. It's part of this thing right here. This common critical values. You see the confidence levels are on there. And here they are to the left. I kind of have them, be careful, I kind of have them going in descending order here. And sometimes it's easy to get confused because they're just so similar looking. You just got to be careful. You know, 0.10 and 0.01 are easy to get confused because they're close, sort of sound close. They're not the same thing, but I have seen many people make that mistake. So now I'm just saying we're going to look at what our decision rules would be for various scenarios here. So if let's say our test is left tail and alpha is 0.05. Left tail automatically means it's going to be negative. So we'll come over here and left tail 0.05, there's our value right here below the box, negative 1.645. So you reject the null if Z is less than negative 1.645. And the next one I made up was right-tailed alpha equals 0.10. 0.10 is the top one. Right-tailed is right below the box, 1.28 positive. Right-tailed would always have a positive critical value. So you'll reject the null if your test statistic Z is greater than positive 1.28. The next case here is two-tailed alpha 0.01. Down here at the bottom, 0.01. See right below the box, have the plus and minus. Let me zoom in on that a little bit, maybe see it a little better. Yeah, see, always plus and minus for two-tailed. Okay. So you would reject the null hypothesis if your Z is less than negative 2.575 or greater than positive 2.575. Now, here's a way to do this in the calculator, and of course I'll show you the reverse table lookup process here. That'll be fine too. But suppose we wanted to find the critical value for some alpha that's not 0.01 or 0.05 or 0.10. Obviously you want to use that little handout I showed you on the other page, that chart for those values. You shouldn't calculate those. But let's look at if you didn't do it, if we want to do it for a different one. Now, look in the calculator. If you do for left tail, if you do inverse norm of alpha, you'll get the exact answer you need. For right, because it'll be negative. Right-tailed, inverse norm of 1 minus alpha. Now, the two-tailed, I have this plus and minus in front of it. That doesn't mean you put plus and minus in the calculator. You just do inverse norm of alpha divided by 2, and that number is going to be negative, and just realize it's going to be plus and negative or whatever that number is. In fact, even without the calculator, this is the way you'll kind of do it for the reverse table lookup process if you're using the chart. You'll go 0.0, alpha will be your left-tailed, 1 minus alpha will be your right-tailed, and then the plus and minus result of alpha over 2. So let's see what we have here. First example, find the critical value of values. I'm allowing for plural here, for a two-tailed test. We have 2 of them. And the decision rule for a two-tailed test with alpha equals 0.08. Now, for two-tailed, we divide alphas over 2, as I have mentioned right above there. So whether you're using calculator or chart, take your 0.08 divided by 2, it's 0.04. And notice with the inverse norm, I just went ahead and put it all in there as one calculation. The calculator did not spit out plus and minus 1.75. It only gives you the negative. You have to add the positive with it. So you see I kind of copied this from the chart So the closest one to 0.04 is 0.401, negative 1.7 row, 0.05 column, so negative 1.75, but it's minus plus. So your statement is reject the null if decision rule if z is less than negative 1.75 or if z is greater than positive 1.75. Always two regions there whenever it's two-tailed. A decision rule with two ends. Hence the name two-tailed. Here's another one. Find the critical value and the decision rule for a right-tailed test with alpha equals 0.08. So it's still 0.08, but it's right-tailed. Go back up here. What's it say for right-tailed? It says inverse norm of 1 minus alpha or reverse table lookup of 1 minus alpha. So 1 minus 0.08 is 0.92. And here's my two calculator commands for both those examples. Obviously, inverse norm, just do it like that. Well, 1 minus 0.08, you don't have to do that first. But if you do by chart, 1 minus 0.08 is 0.92. So without showing the actual chart, I'll show you the value right here, 0.9207, which is the closest one to 0.92. And you certainly can verify that yourself. That's going to be on the 1.4 row, 0.01 column. So it's going to be, that means your critical value is positive 1.41. Therefore, for a right-tailed test, you will say reject the null if z is greater than positive 1.41. All right, let's look at this example, which is going to use, we'll use critical values to do this. Now, obviously, it can be done by critical values, or it can, the same problems could always be done by p-values. Now, of course, if you want to look at both ways, you certainly need to reach the same conclusion. There's never a scenario where you would reject by one method and fail to reject by the other. That would just mean you did something wrong if that happened. All right, let's look at this one. The CEO of a firm claims the mean workday of the firm's office staff is more than 8.5 hours. Random sample of 35 of the office staff has a mean workday of 8.8 and a standard deviation of 0.5. At alpha equals 0.01, test the CEO's claim using rejection regions and critical values. So more than gives you more than as the alternative. That's the claim. The null would be less than or equal to, because that always pairs up with greater than. Less than or equal to and greater than is a right-tailed test, which, let's see, I'm going to copy this from up here. So let's slide that right back in here. All right. So let's look at all my sample data I have written in here. And it's 35. X bar is 8.8. Standard deviation is 0.5. And alpha is 0.01. So now let's identify my decision rule. Right-tailed test. So you always identify your decision rule as greater than a positive test statistic. So 0.01, right-tailed, comes from that sheet that I'll be providing. We don't have to do, you could do the inverse norm, but like I said, I wouldn't bother if you already know this is going to be given to you. So it's basically right here. Right-tailed, 0.01, it's 2.33. So we will reject the null if our test statistic z is greater than 2.33. I kind of drew a picture over here so we could see. So if it's greater than that number, we'll reject. If it's less than that, we'll fail to reject. So let's see what I have over here. I have my x bar as 8.8 minus my hypothesized mean of 8.5 divided by 0.5 over the square root of 35, which I got as 3.55. Now, if you want to run the z-test program to get your test statistic, you can certainly do that. As you can see, I did that, and it gives me 3.55. All right, so how do we make a decision using this method? Well, come over here. 3.55 is greater than 2.33, so it's out there in this shaded region, the rejection region. Therefore, we reject. So we would reject the null and support the claim that the mean workday is more than 8. Oh, that's a typo here. It should be 8.5 hours. All right. And like I said, even though we were using critical values, we'll just take a little peek at the p-value just because it's sitting there. P-value times 10 to the negative 4 means there's 3 zeros in front of it, so it's 0.000193, and that's clearly less than whatever our alpha was, 0.01, or yeah, when you have 3 zeros in front of your number and a p-value, you're going to be smaller than alpha for sure. Now, a coffee shop claims that its fresh brewed drinks have a mean caffeine content of 140 milligrams per cup. Of is equal. Is and of are the two equals. So you see that's our claim, 140. And therefore the alternative would have to be not equal to 140. So we have a two-tailed test. And I have my sample data written over there to the right. Oh, I didn't look at the rest of the problem there, did I? Let's see. We want to test this claim. We have a sample of 42 cups. The mean caffeine content was 146 milligrams with a standard deviation of 22. At alpha equals 0.05, do you have enough evidence to reject the shop's claim? Well, let's see. So we will look at our decision rule and calculate our test statistic, and we'll see. So two-tailed, you're always going to have a double-sided decision rule like this. So two-tailed, 0.05, back up to here. Where's that coming from? Right here. There's two-tailed, 0.05. Plus and minus 1.96. Always two answers for the two-tailed. So our statement always starts out with rejecting it less than the negative. So we have reject the null hypothesis if z is less than negative 1.96 or if z is greater than positive 1.96. So I kind of drew the shaded area. So if it falls in either one of those regions, it's reject. It won't fall in both of them at the same time because the test statistic can't be two numbers. It's either going to be positive or negative. So let's see what we have here. X bar is 146 minus the hypothesized mean of 140 divided by 22 over the square root of 42. Which I calculated as 1.767. So you see I drew right here about 1.767. Now you're only dealing with the positive side. You can ignore the negative. So it's definitely not greater than 1.96. So therefore it's between the two numbers. And that's what you call your fail to reject zone. So we don't reject it. And here's the result of the z-test. And there's your 1.77 from the z-test statistic. And the p-value, same thing, 0.77, which is greater than alpha 0.05, which looks like that's what I'm mentioning right down here below. So you see that also yields to fail to reject. Like I was saying earlier, they have to reach the same conclusion. You can't have reject one way and fail to reject the other. That would be incorrect. Okay. Let's see what we have here. Yeah, so in actuality, like I was kind of saying earlier, that's our conclusion. We fail to reject. But that just, in other words, it doesn't necessarily mean that we agree with their claim statement here, and we certainly don't disagree with it. That's the idea. We don't feel that it's necessarily wrong, whether or not we totally agree it's right, but we don't have to make it that confusing. So, as far as on an exam, just be aware how to do any of these components, because sometimes, instead of asking for all the stuff in one problem, I might ask, one problem, just calculate the test statistic, and you'll certainly have problems where you have to read it and set up the right hypothesis statements, or identify left-tailed, right-tailed, two-tailed, or calculate the p-value. And then I'm sure I'll have a problem or two where it says find the p-value and then make your decision. So it might be like this one could have said p-value is 0.077, fail to reject, 0.077, reject, and then two other p-values that would not be right, but so at least if you got the right p-value, you would narrow it down to one of two answers, and then you could decide whether or not to reject. Then you have to pay attention to whether it's greater than or less than. So we just have to be aware of any possible components of that problem, and then we're pretty much covered for anything on a test. Fast food outlet claims that the mean waiting time in line is less than 3.5 minutes. So less than, that's an alternative. That is, pairs up with greater than or equal to. We have a left-tailed test, since the ha is pointing to the left. Let's look at my test statistics, or sample results that will lead to the test statistic. N equals 60, sample size 60 customers, have a meeting time of 3.4 minutes. And X bar is 3.4, sample standard deviation is 0.6, and alpha is 0.05. So let's look at our decision rule. It's a left-tailed test, so that means our critical value for sure is negative. And without going back up to that little chart for those three critical values, but it's one of the ones that you have, 0.05. The left tail value is going to be negative 1.645. So you would reject the null hypothesis if the z is less than negative 1.645. So let's see what we have. So our sample mean is x 3.4. So like I said, we have to be careful not to get these two values in the numerator reversed. 3.4 is the x bar, minus 3.5, which is the hypothesized mean, divided by 0.6 over the square root of 60. So that gives us the test statistic of negative 1.29. Now I kind of drew a little picture here. Sometimes it can be trickier with the negatives. Negative 1.29 is not less than negative 1.645. In other words, it's not to the left of it on the number line, it's to the right. So for a left-tailed test, if you're to the right of the number, you're in the fail to reject zone. We're not in the rejection zone. So there's my value. You see the arrow pointing right there. So sometimes the picture might help. Of course, like I said, you could put this in the calculator and get the p-value if you want to, which I think I'll do that real quick just to show you can verify at least the rejection part of this. But okay, let's see what we have. Stat test z-test. We're claiming 3.5. Standard deviations 0.6. X bar is 3.4. N is 60. And it's left-tailed, I believe. Yeah, left-tailed. So I pick an alternative to the left, which is right there. Hit calculate. Get the little box out of there. Alright. Copy. Paste. Let's see. kind of shrink that down a little bit. It's not too obtrusive, but so you see we got our test statistic correct, negative 1.29. There's the p-values a backup. The p-value 0.098 is greater than whatever that was, 0.05, so that also leads to fail to reject. All right, that concludes this section. Next section, we will be looking at hypothesis test for the t-test statistic for small samples.